In this video, we're going to talk about the theory a little bit behind doing what are referred to as goodness of fit test. So the scenario here is that you have taken a random sample and you're trying to determine whether or not some model is a good model, some distribution is a good model for the probability distribution for this particular population that you took the sample from. So we're going to do a couple of straightforward examples in this video, and then we're going to talk about some more complicated examples using Excel when we talk about it in class time. So to get a little bit of the theory behind things, let's start with a pretty easy setup. Let's say that we have a random variable. I'm going to refer to it as y1 here, is a binomial random variable where we have n trials and the probability of success, here denoted by p1. That's our probability of success in this case. So then we know from the central limit theorem that if we take y1, subtract off n times p1, which is, of course, the expected value of y1, and then divide by the square root of n p1 times 1 minus p1, the standard deviation of y1, we get something that's approximately normal. We know from what we've talked about before that typically we want n times p to be bigger than 5 and n times 1 minus p to be bigger than 5 to make sure that this really is close to a normal distribution. The book even mentions, though, for what we're going to use this for, that as long as n times p is at least 1, this is going to be a pretty good estimator for us to talk about how we can do goodness of fit tests. So in general, as long as that n times p is not exceptionally small, this is going to be a good test for us to be able to determine goodness of fit, whether or not a particular probability distribution is a good one to model the probability distribution of the population that we're talking about. And we'll talk about why we want that n times p to be a decent sized number and not to be a very small number here in a minute. All right, so we know from stuff that we've talked about before that if we square a standard normal, we get a chi-squared distribution with 1 degree of freedom. So this particular distribution has chi-squared of 1 degree of freedom. All right, so let's play with the format of this particular distribution just a little bit. For simplicity's sake here in a minute, for notational sake, I guess I probably should say, we're going to let y2 be n minus y1, and we're going to let p2 be 1 minus p1. So if y1 is actually representing successes, we count the number of successes in n trials, then y2 is counting the number of failures. If p1 is the probability of success, then p2 is the probability of failure. All right, so we know that z squared is just, of course, here squaring the z up here, so it looks like this. I can play with the algebra just a little bit. This is 1, of course, times this, so I can take it as 1 minus p times it, and then plus p times it. I guess I should say p1 in both cases. And then split the fraction and simplify, and I have y1 minus n times p1 squared over n p1, and then y1 minus n p1 squared over n times 1 minus p1. Probably trying to figure out at this point why we're splitting this up in this fashion. Notice that in the second denominator here, I have a 1 minus p1, which is our probability of failure. And then notice in this first fraction here, I've got expected value here, and I've got expected value in the denominator. Also notice that this would be your expected value of the number of failures. This is expected value of number of successes. So to continue along those lines, let's play with that second fraction. So if I do y1 minus np1, well, I can add and subtract n on the inside. I can factor out a negative, and then in the second two terms, factor out an n, and I'm left with n minus y1 minus n times 1 minus p1. Well, if I square both sides, notice that y1 minus np1 squared is equal to y2 minus np2 squared. In particular, notice that this is the expected value of y1, this is the expected value of y2. And I can replace this in the numerator in the second piece. So we now have z squared, which I see I have 2 pieces here, is approximately chi squared of 1. The thing that I want you to notice out of this before we go on to a more complicated setup here is that notice that we've got two summands, but we've lost a degree of freedom essentially. And the reason for that is, of course, that once I know number of successes, I automatically know number of failures. So I don't really get a degree of freedom over here. This y2 isn't independent of the y1, right? It completely depends on what y1 is. All right. So this is what I just mentioned again. Notice that the NP1 is number of successes and NP2 is the number of failures. So for notational sake, let's say our Q1 here is just the summand from 1 to 2 in this case. If we truly have that binomial distribution that we started with to start at the beginning here, then we would expect that both of the numerators that we have to be small. We would expect that our number of observations we have for y1 should be close to its expected value, and we should expect that the number of observations that we have for failures should be close to its expected value. We would expect that to be small, and we would want that, and then that of course would make our Q1 close to 0. Now, hopefully you're understanding why I mentioned before at the beginning why we want to make sure that n times p idea is not really small, because if it gets really small, it could make this be abnormally large and skew things when we don't want them to be skewed. So we want to make sure that this particular probability isn't too small, because it's going to have an undue influence on the statistic that we're going to be calculating. So that's our main reason why we want to make sure that n times p is not too small. All right, then likewise, if our distribution of y1 is different from a binomial distribution, then we would expect that y1 not to be close to that expected value, because this expected value is coming from a binomial. So if this is not binomial, we wouldn't expect this expected value to necessarily be close to the y1, so we would expect it to be large, that Q1 to be large, in some relative sense. In the relative sense, I mean, is what we expect the distribution of the Q1 to be. All right, so let's look at a specific example, try to make this thing a little bit more clear from a concrete example. Let's say you do the classic binomial experiment, you flip a coin, and we're going to do this, say, 200 times. And say you flip the coin 200 times and you observed a head 125 of those 200 times. Do you think the coin is fair? All right, so of course, if the coin's fair, then our P1 and our P2 here is 0.5, so we would expect to see 100 heads and 100 tails. Expect that since we've seen 125 heads, we saw 75 tails, so just plugging these in, if we do these calculations, we're doing the observed value minus expected value squared over expected value. This is for successes. Observed value minus expected value over expected value for failures. We get 12.5. So of course the question is, if y1 is in fact a binomial distribution on 200 trials and probability of success a half, is this really an unlikely value to have from a chi-squared of 1 distribution? Recall that Q1 should have approximately a chi-squared of 1 distribution, if this is in fact true. Well, if we use Excel or use a table, we see, well, actually, we use Excel to figure this out. The table's not going to help us too much. We could use a table to find a critical value. But we use Excel, we find that the probability that being bigger than 12.5 is, 4/10,000ths about? So yes, this is a very unlikely value to have occurred. It's way far outside of what we would expect to have happen. So we would conclude this is probably not a fair coin. So this is how we use this chi-squared goodness of fit test to help us out with this. So, all right, so let's see if we can make this a little bit more formal and then generalize it a little bit. So let's say we have an experiment, not with just mutually exclusive outcomes, just 2, but let's say we have k mutually exclusive outcomes, so that any observation has to fall into one of the outcomes. So what I mean by that is that we've got k different possibilities for outcomes, so I'll label them A1 through AK. Mutually exclusive means, of course, there's no overlap, so any A sub I intersect A sub j is empty, of course, provided that I is not equal to j. And then if I do the union of all of these, this is the must fall into one of the outcomes. The union of all of these actually takes up our entire sample space S. All right, so let's let the y1 out to yk count the number of observations that fall into each of the possible outcomes And let's assume that each of these are going to be observed over n independent and identical trials. So let's let the p sub i's here represent the probability, each of the probabilities that an observation falls into the respective outcomes. So p1 is a probability that falls in a1 and so on down the line. If that's the case, then our n times p1, n times pi, of course, is the expected value for a particular y sub I. So if we do that same type of computation that we did in the two outcome case, if we do that same kind of computation where we take observed y sub I minus expected np sub I, square it, and then divide it by expected, sum it up, that should give us approximately a chi-squared on k minus 1 degrees of freedom. Now, just intuitively thinking about why it's the degrees of freedom is k minus 1 instead of k, notice we're adding, oh, this should be a k not here on the top of the summation, not an n. So if you're writing this down in your notes, this should be a k here that I'm circling with the mouse. That should be a k up there on my summand. So why should be a k minus 1 degrees of freedom instead of k is because, well, what you might be thinking it should be k is because usually when you're thinking about adding up independent chi-squared random variables, you get a chi-squared random variable on that many degrees of freedom, how many ever things you added up. However, notice that we don't have independence for this last one. Once we know the y1 onto y sub k minus 1, we automatically know what y sub k is. Because remember, all the trials have to fall into one of the possibilities. Well, if I know what all the possibilities are up to k minus 1, then I automatically know that the leftovers are left in y sub k. So the distribution of the q sub k minus 1 only depends on the y1 to y sub k minus 1, which is why we use k minus 1 here, even though this top index up on the summation there should be a k. All right. So what we're going to do is we're going to test whether each probability is equal to a known value. So our null hypothesis looks like p sub I is equal to some p sub I naught, where I goes from 1 to k, and we're going to test it against all possible alternatives. So let's do another example, pretty classic example, of course, where we're going to roll a die, a six-sided die, I should say. Let's say it's rolled 102 times, and then we have those results that were recorded. So the question here is, does the die to appear fair? And let's use an alpha that's equal to 0.05. So making this a little bit more formal for a null hypothesis, and I just put the outcomes up here just for reference. The null hypothesis is that each probability is 1/6 from 1 to 6. We notice that the expected number of observations is 102 trials times a 6 for each of them, so all of them are going to have an expected value of 17. All right, so this computation will be our test statistic. This random variable looks like our test statistic. So we know that this is supposed to be chi-squared of 5, or approximately chi-squared of 5, if this should be a fair die, right? This should be, when we do this computation, this should be a chi-squared random variable. So what gets to be too big for a chi-squared of 5 random variable? Well, if we do the critical value based on an alpha value of 0.05, we're going to reject if the value of the test statistic that we're going to calculate is going to be greater than the 11.07 number. So here's our test statistic. We use the capital Y, of course, to represent the random variable, and the little one to represent our actual observations. So the test statistic here is going to be, we take each observation minus its expected value, square it, and then divide by the expected value. All of the expected values are 17, so that's why those all look the same here. We plug in each of those values, and we get 3.765. So in this case, we do not reject the H0. So there's not enough evidence to conclude the die is not fair. And in fact, if we look at a p-value associated with that particular test statistic, we notice that the probability of being greater than that particular test statistic is 0.58. That's a pretty large probability, right? So there's no reason for us even to suspect that the dice might not be fair, right? So we'll do more of this with some actual data on Monday. We'll be using Excel extensively to be able to do this, so we're not doing these computations by hand. But I wanted to give you a little bit of an introduction of what's going on before we start doing it with more complicated examples, and then talking even a little bit further about how our degrees of freedom end up getting reduced even more when we start estimating parameters for particular probability distributions instead of the probabilities that I've already given to you. So we'll talk more about this on Monday.